3 hours of light. That is often enough for a yield. Most growers abandon the northern walls or the space under heavy tree canopies. They assume the soil there is dead capital. This is a calculation error. Why assume shade is a barrier? For specific species, it is a requirement for survival. Understory plants evolved to capture scattered photons with extreme efficiency. Their leaves are often darker and wider, designed to absorb every available unit of energy. In direct sun, evaporation is rapid. The crop wastes resources pumping water just to cool its tissues. In the shadows, the dynamic changes. Humidity lingers near the roots. The plant focuses its metabolism on fruit production rather than fighting heat stress. On the surface, the garden corner looks dim and dormant, but inside the cellular structure, sugars are accumulating steadily. The soil remains cool to the touch. Dark green foliage acts like a solar panel optimized for low light. While standard crops burn under 12 hours of radiation, these species occupy the niche of the forest floor. They do not just exist, they thrive. The unutilized space turns into a functioning production unit. Here are 20 reliable varieties to colonize the shade. 4 hours of sunlight. That is the biological minimum required to generate a harvest here. Why do most commercial crops fail in the shade? They lack the energy to set fruit. But the raspberry utilizes a specialized adaptation for low-light environments. Specific cultivars have evolved to bypass the need for solar saturation. Varieties known as Polka and Glen Ample function efficiently with limited photon exposure. In zones 4 through 9, this plant finds its niche in the marginal spaces. It occupies the cooler perimeter of a tree canopy or the darker, north-facing side of a structural barrier. The plant does not just survive here, it optimizes its metabolism for the shadows. Direct afternoon radiation acts as an enemy. Intense heat causes thermal stress, curling the leaves and desiccating the developing fruit. The shade serves as a protective shield. It preserves moisture content within the cellular structure of the berry. On the surface, the environment seems energy poor, but inside the cane, the sap flow remains consistent. The result is a higher liquid-to-pulp ratio and a denser flavor profile without the scorching damage of the sun. Colonization happens rapidly. Growers introduce the crop as dormant canes or utilize runners to expand the footprint. Underground, the root system spreads laterally, acting like a net to capture nutrients. In accelerated motion, green shoots erupt from the soil surface, expanding upward to intercept filtered light. But maintenance is critical. Biological mass accumulates without pause. Without mechanical intervention, the patch becomes an impenetrable thicket of tangled wood. Pruning is mandatory. Once the fruiting cycle concludes, the old canes are removed. This removal triggers a hormonal response in the root crown, forcing new, vigorous growth for the next season. The return on investment is high. Fresh consumption provides immediate glucose. Preservation allows for a long-term calorie stock, a sustainable food source secured from the darkest corner of the territory. 4 hours of direct sunlight, that is the minimum threshold for this biological machine to function. Why do most commercial fruit trees fail in the shadows? They starve for solar energy. But the plum tree operates differently. It is built for efficiency. While other species demand full exposure, many plum varieties will set fruit reliably with just 4 to 6 hours of light. The strategy relies on selecting compact or dwarf genetics. In limited space, height is an enemy. Dwarf varieties solve this logistical problem. Instead of wasting resources on massive timber and an oversized canopy, the tree redirects sugars. The goal is fruit production. Every calorie goes into the blossom rather than the wood. Placement is a calculation of angles. These smaller trees fit easily near buildings or under the canopy of larger vegetation. Timing is critical. The ideal location offers morning sun. The first rays hit the leaves. The heat evaporates the night dew within minutes. This is not just drying. It is a sanitation protocol. By removing moisture early, the plant prevents fungal spores from taking hold. On the surface, The afternoon shade looks like a disadvantage, but inside the cellular structure, it is a relief mechanism. Cooler temperatures prevent heat stress. The tree does not need to pump gallons of water just to keep its leaves from scorching. Adaptable genetics are key. Varieties like Santa Rosa survive where others fade. In tight urban corners or dappled light, these cultivars maintain output. But biology needs assistance. Architecture determines success. You must act as an engineer. Once a year, prune the branches. The center must remain open. This creates a solar funnel. Light penetrates deep into the canopy, striking the dormant flower buds hiding on the inner wood. Remove crossing shoots. Chaos blocks photosynthesis. Better light penetration results in higher bloom quality and consistent yields. The return on investment is high. The fruit is dense with sugar and water, a purple skin that snaps under pressure, yellow, sweet flesh inside. Perfect for immediate consumption or long-term preservation in jams. One basket provides calories for weeks. Maintenance is low impact. In cooler zones, cover the root system with organic mulch. This stabilizes soil temperature, water deeply but infrequently. Force the roots to dig down. Feed lightly in early spring. Nitrogen drives leaf growth, but too much creates a jungle without fruit. Balance is the objective. If the site lacks full exposure, this is the solution. Select a compact variety. Control the structure. Even in the shadows, the harvest is guaranteed. Reliable blossoms guarantee caloric density. Sweet fruit emerges even where solar energy is scarce. The next biological machine capable of thriving in partial shade is the fig. Why does a Mediterranean crop accept the shadows? It seems counterintuitive, but biologically, the fig is surprisingly adaptable. While the metabolic processes prefer high heat, the plant secures a healthy yield with only 4 to 6 hours of direct exposure daily. This is most effective if the photons strike during the morning hours. In scorching climates, the deficit of afternoon sun becomes a tactical advantage. Intense UV radiation burns cellular structures. Shade acts as a shield. It prevents leaf scorch and stops the sugars inside the fruit from fermenting or the skin from cracking due to thermal stress. The fruit retains its integrity. Specific genetics matter. The Chicago Hardy variety is evolved for USDA zones 6 through 10. The structure is compact. It fits within the limited cubic volume of a mobile container. This offers a logistical edge. If the solar angle changes, the grower simply relocates the unit to capture the available light. There is one crucial biological nuance. Most fruit trees require a partner for genetic exchange. The fig is self-pollinating. A single organism is a complete production line. No insect vectors or cross-pollination partners are required to convert energy into edible biomass. The substrate dictates survival. Plant them in loose, well-drained soil matrices. Water management is critical. On the surface, the plant looks robust, but underground, stagnant moisture suffocates the root hairs. The fig demands oxygen at the root level. Hypoxia leads to rapid systemic failure. Seasonal transitions require intervention. The wood endures light frost. However, in aggressive cold zones, thermal insulation is mandatory. Growers wrap the trunk or move the container to a temperature-controlled storage unit to prevent cellular freezing. In fast motion, the sap rises as temperatures climb. The best yield does not form on old bark. It erupts from new wood. Strategic mechanical damage, light pruning in late winter, signals the plant to regenerate. This triggers a surge of fresh growth and maximizes fruit density for the next cycle. Few crops offer such a high return on investment in partial shade. The fig is a drought-tolerant survival asset. It requires minimal labor input. In return, it delivers concentrated sugar energy, even when the sun only strikes for a fraction of the day. 3 hours of direct sunlight. That is the minimum requirement for growing sugar in the shadows. Why prioritize the lowbush variety over its taller cousins? Highbush types demand full solar exposure to function. But the lowbush blueberry utilizes a different survival strategy. It thrives in light deprivation. While standard commercial crops fail without 8 hours of sun, this plant is engineered for the forest floor. It targets USDA zones 3 through 7. Here, cooler summers and filtered light replicate its natural woodland environment. Upon closer inspection, the growth pattern reveals an aggressive mechanism. It does not just stand there, it spreads. Underground, a network of rhizomes pushes horizontally through the dirt. These runners colonize the soil, sending up new shoots every few inches. It forms a dense living carpet of fruit-bearing foliage. It functions effectively as a productive ground cover beneath the canopy of taller trees. But biology needs chemistry to function. On the surface, the soil might look fertile. But inside, the chemistry must be specific. Success relies entirely on pH levels. The target is strict, between 4.5 and 5.5. If the ground is neutral, the plant starves. You must intervene. Peat moss, pine needles, or elemental sulfur are introduced to drop the alkalinity. Mulch is applied heavily using pine bark or sawdust. This is not for decoration. The root system is dangerously shallow. Without a protective layer, the delicate fibers dry out and die. The mulch locks in moisture and mimics the forest floor decomposition process. The result is a steady caloric output. Even in partial shade, the plant manufactures glucose. The yield consists of small, dense berries. The taste is specific: sweet, tart, concentrated. Ripening might lag behind crops grown in full solar radiation, but the flavor profile remains intact. In accelerated motion, the seasons transform the plant structure. Spring brings clusters of white, bell-shaped flowers. They drop. Green berries swell. Then, as temperatures drop, the chlorophyll degrades. The foliage turns a brilliant warning red. This is a crop that brightens the dark corners of a plot while securing a harvest where nothing else will grow. "4 hours of direct light. That is the minimum requirement for a caloric powerhouse. Why push a crop into the shadows? Usually, yield drops without full exposure. But with the blackberry, the lack of scorching heat triggers a different survival response. This species is aggressive. It does not ask for perfect conditions. It seizes territory. While delicate crops stall without 8 hours of radiation, the blackberry adapts. 4 to 6 hours of solar exposure is sufficient to trigger flower production. Up close, the difference is visible on the skin of the fruit. In full sun, intense solar radiation evaporates surface moisture, shrinking the biomass. The fruit becomes tough. In the shade, evaporation slows. The individual droplets swell with retained water. On the surface, less light seems like a structural disadvantage. But inside the cellular structure, water retention increases. The result is a harvest defined by hydraulic pressure. The berries become heavy, dark black, saturated with fluid rather than dried out by ultraviolet exposure. This is biological efficiency. However, genetics play a crucial role in this equation. Modern cultivation relies on specific engineered strains: Triple Crown, Arapaho. These are thornless varieties, stripping away the plant's natural defense mechanism to facilitate rapid harvesting. Labor becomes efficient. No protective gear is required to access the nutrient source. These cultivars operate effectively across USDA zones 5 through 9, covering a massive climatic swath of the continent. The growth habit is chaotic but trainable. Growers often guide the canes onto wire trellises, creating a vertical, two-dimensional wall of fruit. Alternatively, the plant is left to its own devices. It forms a dense, impenetrable hedge. It becomes a biological barrier that blocks sight lines and restricts physical access. There is a mathematical nuance here. In partial shade, the plant generates fewer total canes. The density of the thicket drops, but the biomass shifts. Energy is diverted from vegetative expansion directly into the reproductive organs. The berries that do form are significantly larger. The ideal logistical setup involves morning photons followed by structural shade in the afternoon to prevent thermal stress. Maintenance requires a strict understanding of the life cycle. The cane grows 1 year, fruit the next, and then dies. It becomes dead weight. To maintain the output of this open-air factory, the grower must mechanically excise the spent wood. Space must be cleared for new shoots. At ground level, a heavy layer of mulch seals the soil surface. This suppresses competing weeds and locks in the water table during critical flowering stages. In accelerated motion, the white blossoms give way to green fruit, which darkens rapidly to black. The plant is resilient. It grows fast. The shaded corner ceases to be dead space. It becomes a consistent, calorie-dense asset. 4 hours of direct photons. That is the minimum energy requirement for a biological reactor often dismissed by growers, the pear tree. Why position a fruit-bearing organism in the shadows? Conventional logic dictates that maximum yield requires maximum exposure. But in practical agronomy, the pear negotiates a different contract with the environment. It is far more adaptable than common knowledge suggests. With only 4 to 6 hours of sunlight daily, the mechanism still activates. Most varieties trigger their flowering cycles, successfully set fruit, and deliver a calculated, dependable harvest every season. In warmer latitudes, shade is not a handicap. It is a strategic advantage. Pears prefer the lower temperatures of the morning. They tolerate significant obstruction in the afternoon. This specific light pattern performs a critical function. It reduces thermal stress. By limiting exposure during peak UV intensity, the canopy prevents sun scald, a physiological disorder that burns the skin of developing fruit and destroys its structural integrity. Standard cultivars like Bartlett or Anjou demonstrate high reliability across United States Department of Agriculture zones 4 through 9. The genetics are robust. For sites with limited acreage or partially obstructed perimeters, dwarf and semi-dwarf rootstocks offer a geometric solution. These compact units fit into spaces where standard timber would fail to mature. On the surface, the tree seems merely to survive in the shade, but inside, it builds a caloric infrastructure capable of outlasting the planter. The logistical value of this species lies in its longevity. Once the root system anchors into the subsoil, the organism becomes a fortress. It is tough. It is disease-resistant. It operates as a food production facility for decades. The output is equally durable. Pears store for months under proper refrigeration. In a resource-restricted scenario, this is not just a sweet snack. It is a stable calorie reserve that remains edible long after soft fruits have rotted. Cultivation in partial shade requires precise intervention. Canopy management becomes critical. Pruning is not aesthetic. It is structural. You must surgically remove excess wood to keep the center open. This ensures airflow, preventing fungal pathogens from colonizing the damp leaves. It also allows every available photon to strike the inner branches, guaranteeing even ripening. Up close, the clusters of young fruit appear dense. This triggers a necessary culling. In midsummer, manual thinning is required. Removing the excess load allows the remaining pears to size up properly. The skin stretches. The pulp accumulates sugars. Without this calculation, the crop remains undersized and fibrous. At ground level, a layer of mulch seals the surface. This retains essential soil moisture. During dry spells, deep irrigation drives water down to the taproot. The efficiency is startling. You will be amazed at the tonnage a single tree can generate without full solar exposure. If the objective is a low-maintenance asset that converts shade into food, the pear is the optimal choice. 3 to 5 hours of light. That is all this organism requires to function. Item number 7 on the list is the currant. Whether the genetic expression results in black, red, or white pigment, the mechanism remains the same. These are compact shrubs designed for survival in light-deficient environments. Why does this plant reject the open sun? Its biological origins trace back to cool northern climates. Intense solar radiation burns the foliage. Therefore, partial shade is not a limitation. It is a biological necessity. The optimal growing range lies within United States Department of Agriculture zones 3 through 7. Here, the plant efficiently converts limited solar energy into ascorbic acid. The concentration of vitamin C in these berries rivals citrus fruits. The flavor profile is strictly functional. It is tart, sharp, acidic. This makes the harvest ideal for long-term preservation in jellies or heavy syrups. Upon closer inspection, the varieties differ significantly. The Rovada red currant produces long chains of bright, translucent berries. The skin is thin and snaps under pressure. In contrast, the Benzarek black currant is built for durability. Its flavor is deeper, used primarily for potent cordials. But the true logistical value lies in spatial efficiency. In a mature garden, large trees monopolize the sunlight. Most crops starve in this shadow. Currants utilize this dead zone. They function as an understory layer, colonizing the space beneath the canopy. The soil requirements are specific. The earth must be dark and porous. Water retention is critical. The roots demand constant hydration, but cannot tolerate standing liquid. In the spring, a resupply of organic compost provides nitrogen. A thick layer of mulch acts as a thermal barrier. It keeps the underground system cold, even as the ambient air heats up. Maintenance follows a strict protocol. Pests rarely attack the bitter foliage. Disease resistance is high. However, the plant requires mechanical intervention. Once a year, the pruning shears must come out. Old wood stops bearing fruit. The stems turn gray and rigid. By removing these exhausted limbs, the grower forces the shrub to redirect energy. New shoots emerge from the base. Fresh green wood replaces the old. This is where the yield concentrates. Even in the darkest corners of the plot, production continues. The shrub requires minimal labor, but delivers dense caloric value. The return on investment is high. Item number 8 on the list is a fruit that reaches its peak performance during the autumn season. Three to 5 hours of light. That is the absolute maximum this biological machine requires. Why does a fruit-bearing plant reject the sun? Most crops treat solar radiation as fuel. For the gooseberry, direct exposure acts as a stressor. Intense rays scorch the cellular tissue of the leaves, halting production. This shrub is engineered for the shadows. Closely related to the currant, it dominates the understory layer in USDA zones 3 through 8. This covers a massive geographical footprint. The mechanism is efficient. Varieties like Invicta or Hinonmaki Red are not selected for aesthetics. They are chosen for industrial-level output and disease resistance. The yield is consistent. Up close, the fruit reveals a thick, translucent skin. Colors shift from pale green to deep red or heavy gold. Inside, the pulp is dense. High concentrations of pectin provide natural structural integrity. This chemical property is crucial for long-term preservation in jams, but the root system needs support. The soil must be nutrient-dense and free-draining. A thick layer of mulch is not optional. It serves as a thermal regulator, keeping the underground network cool while blocking invasive weeds. The roots cannot compete for resources. The ground must remain clear. On the surface, it appears to be a simple bush, but closer inspection reveals a perimeter defense system. The branches are armored with rigid spines. This physical barrier deters herbivores effectively. Rodents approach, encounter the thorns, and retreat. The harvest remains secure without human intervention. Space requirements are minimal. These plants slot into narrow margins where standard crops fail to photosynthesize. Maintenance is low cost. Simply remove the exhausted canes every few years. This triggers a biological reset. ensuring production cycles continue for decades. Three hours of sunlight. That is the minimum requirement for survival here. Why plant where the sun barely reaches? Most commercial crops wither in the dark, starved of energy, but the elderberry treats shadows as an asset rather than a liability. This is not a delicate garden ornament. It is a native biological machine built for the understory. While fragile species demand full solar exposure to function, the elderberry biomass engages highly efficient photosynthesis with limited photons. It seizes territory that other plants abandon. Seen in fast motion, the root system expands aggressively, anchoring into soil ranging from rich loam to waterlogged clay. This adaptability makes it a strategic asset in USDA zones 3 through 9. The plant tolerates saturation levels that would rot the roots of a standard fruit tree. Varieties like Adams and York are favored in practical agronomy for their sheer reliability. They do not just grow, they colonize. Underground runners shoot outward, breaching the surface to form dense living walls. A single planting evolves into a fortification against erosion. By the height of midsummer, the structure supports heavy biological output. On the surface, luscious clusters of fruit, but inside the raw berry, a chemical defense mechanism waits. Ingestion of raw elderberries triggers immediate gastric distress. The plant protects its seed with toxicity, but heat neutralizes the threat. Boiling transforms the deep purple clusters into high-value glucose syrups, fermentation bases for wine, and caloric jams. The utility extends beyond the fruit. Before the berries set, the white flowers are harvested, dried for infusions, or extracted for cordials. Every stage of the life cycle offers a resource. There is a paradox in cultivation here. Logic suggests that more sun equals more energy. However, direct solar radiation often strips moisture from maturing fruit through rapid transpiration. In the partial shade, evaporation slows down. The berries retain water mass, swelling to a larger size with higher juice content. The biology favors cool environments over scorching heat. To maintain this output, human intervention is required. The grower must excise old wood annually. Upon closer inspection, the bark on aged canes turns gray and brittle. These exhausted stems consume nutrients without returning a yield. Cutting the dead weight stimulates the emergence of fresh green shoots. The cycle resets. Dark corners of the cultivation zone become calorie-dense resource hubs. The harvest is secured for decades. Three to 5 hours of light. That is the only fuel requirement for this biological machine. Most crops demand full solar exposure to generate sugar, but the serviceberry, known regionally as the Juneberry or Saskatoon, operates on a different set of rules. It is a native North American engine disguised as a decorative shrub. Why does it thrive where standard agriculture fails? Because it evolved in the shadows. In the wild, this plant functions as an understory tree, seizing territory beneath the canopy of massive forest giants. It does not fight for the sun. It adapts. The geographical range is immense. This species secures territory from USDA Zone 4 all the way to Zone 9. It withstands freezing winters that would shatter less hardy plants, and it tolerates the reduced luminosity of partial shade with indifference. This makes it a strategic asset for growers dealing with established tree lines or north-facing walls. The plant utilizes space that industrial logic would usually classify as dead zones. In accelerated motion, the cycle is relentless. White blossoms erupt in early spring, signaling the end of dormancy. By early summer, the branches sag under the weight of the yield. By autumn, the foliage turns a burning red. On the surface, it appears to be a simple ornamental bush. But inside, the root system is extracting moisture to pump water into dark, purple berries. To optimize this production, the logistics are simple. The soil must be well drained. A layer of mulch acts as a thermal regulator, retaining groundwater and protecting the roots during the heat spikes of midsummer. There is one nuance here. Survival is possible in deep shade, but maximum output requires calculation. A specific dose of morning light acts as a catalyst. It triggers the chemical reactions necessary to boost sugar content and increase the physical diameter of the fruit. The result is a berry that rivals the blueberry in taste and texture. The harvest is versatile. It provides immediate calories when eaten fresh, or it can be processed into pies and preserves for long-term storage. However, the grower faces aggressive competition. Avian populations track the ripening process with precision. Birds treat the serviceberry as a primary food source. Without the installation of physical barriers like protective netting, the entire crop can vanish within a few hours of maturation. This is a low-maintenance asset. It requires little, yields early, and occupies the margins. It turns the dark, unused corners of a plot into a productive food factory. This is how you monetize the shade. A tropical anomaly in a temperate forest. The 11th specimen on this registry is the pawpaw tree. It is a biological paradox native to the eastern United States. While it possesses the genetics of a cold, hardy plant, the fruit mimics the caloric density of the tropics. Why does a species native to North America taste like it belongs on the equator? Evolution pushed it into a specific niche. The flesh is not fibrous. It is a soft, custard-like emulsion. Upon consumption, the flavor profile registers as a complex synthesis of banana, mango, and melon. Most fruit-bearing trees aggressively compete for vertical space to seize the sun. The pawpaw retreats. It acts as an understory specialist, colonizing the low-light zones beneath massive timber stands. It operates efficiently in United States Department of Agriculture zones 5 through 8. The energy requirement is minimal. Just 3 to 5 hours of filtered light per day is sufficient for photosynthesis. On the surface, the large drooping leaves look like they belong in a rainforest, but inside, the cellular structure is hardened against frost. Early development is critical. For the first few years, direct solar exposure is not a fuel source. It is a stressor that damages the tissue. The plant requires the shadow of the canopy to establish a deep, anchoring root system without dehydrating. In accelerated motion, deep purple blossoms unfold in the spring. They are followed by heavy clusters of greenish-yellow fruit that swell with sugars until late summer. But there is a logistical hurdle here. Most varieties lack the mechanism for self-pollination. A solitary tree is a sterile tree. To secure a harvest, the grower must plant at least 2 genetically distinct organisms in proximity to ensure cross-fertilization. However, exceptions exist in modern breeding. The Shenandoah variety is one of the few capable of self-fertility, bypassing the need for a partner. The underground environment dictates success. The soil must be rich and permeable to water. A thick layer of mulch functions as a thermal regulator, maintaining cool temperatures for the feeder roots. This is a survival crop for difficult terrain. It resists pests. It thrives where citrus dies and stone fruits rot. If the goal is calorie production in the shade, this tree is the optimal biological machine. Let us examine the next fruit that performs in these conditions. Four to 6 hours of sunlight. That is the bare minimum required to activate the biological machinery of the hardy kiwi. While most fruit crops demand full solar exposure, this vine operates efficiently in the shadows. It is a survivalist's choice for the understory. Why choose a vine that mimics a jungle creeper? Because, unlike its commercial cousin, this plant eliminates waste. No fuzzy skin, no peeling, just pure edible biomass. Upon closer inspection, the fruit is smooth and green, roughly the size of a large grape. It is a concentrated packet of energy. You consume the entire unit. In the mouth, the skin snaps, releasing sweet acidic juice immediately. There is no friction, only fuel. The plant thrives in USDA zones 4 through 8, showing a preference for cool morning photons while requiring shielding from the intense afternoon radiation. But do not underestimate the physical load. This isn't just a garden vine, it is a heavy biological engine. Without a steel-reinforced trellis or a thick wooden arbor, the structure will collapse. Once established, the vines thicken rapidly, resembling woody cables rather than delicate stems. The support system must be engineered to withstand tens of kilograms of vegetative weight. In standard cultivation, biology dictates a strict ratio. You need both a male and a female plant to initiate fruit set. The male provides the pollen. The female produces the yield. However, genetics have provided a workaround. The variety assi breaks this rule. It is self-fertile. One plant is enough to start production, making it the logical choice for limited square footage. In fast motion, the foliage spreads laterally to capture every available photon. In partial shade, the leaves may lack the deep emerald saturation of full sun plants, but the mechanism works. Fruit production remains reliable. The grower must act as an architect. New growth is trained along horizontal wires, creating a living solar array. Pruning is not aesthetic, it is functional. In late winter, while the plant is dormant, excess wood is removed. This clears the path for light to strike the developing fruiting spurs. Without this intervention, yield drops. On the surface, it is a passive food source, but underground, the root system is aggressive. It demands consistent moisture. A heavy layer of mulch is applied to lock in hydration and stabilize soil thermodynamics. The roots cannot tolerate drought. There is one nuance here. This aggression has a downside. In parts of the Northeast, the hardy kiwi is not just a crop, it is a classified biological invader. It escapes cultivation and chokes out native flora. Checking local agricultural regulations is a mandatory step before planting. In a controlled environment, however, it behaves. It utilizes vertical space where horizontal land is scarce, turning fences and pergolas into production units. Give it a rigid framework and steady hydration. In return, the plant converts shade into kilogram after kilogram of aromatic, high-density nutrition. Item number 13 on the roster. Technically, this is not a fruit, it is a biological imposter. Rhubarb is defined by botany as a perennial vegetable. While culinary tradition often forces it into sweet pies and jams alongside strawberries, the plant itself is a leaf stalk, cultivated for its sharp, acidic punch. Why does it dominate in the shade? Because heat is the enemy. This plant requires cooler ambient temperatures to function efficiently. 3 to 5 hours of sunlight are sufficient for the metabolic process. It does not demand a full solar cycle. The crop is engineered for survival in USDA zones 3 through 8. However, the terrain matters. The soil must be fertile and drain rapidly. Stagnant water is fatal to the root crown. In practical agronomy, the variety Victoria stands out. It is a shade specialist. It produces dense, heavy biomass even without direct exposure to the midday sun. There is a nuance here regarding solar intensity. Excessive radiation triggers a defensive reaction. The stalks wilt. The fibers lignify, turning the texture woody and tough. Afternoon shade acts as a temperature regulator. It preserves the cellular structure, keeping the flesh crisp and tender. Patience is a resource. In the first year, harvesting is forbidden. The plant is not growing food for you yet. It is building an energy reserve. The root system acts like a biological drill, piercing the clay to reach stability. Only in the second year does the production cycle truly begin. In fast motion, the process is visible. The stems thicken and turn a deep red. When the stalks are rigid and firm, extraction begins. A crucial rule applies to the harvest. Never strip the plant bare. Leaving a percentage of the biomass ensures photosynthesis continues. The organism needs fuel to regenerate for the next season. At first glance, it looks like a simple, leafy green. But there is a chemical trap. One biological hazard exists. The broad green leaves are waste material. They contain oxalic acid, a compound toxic to humans. The edible value is strictly limited to the stems. The rest must be discarded. Maintenance is low but critical. In the spring, a layer of compost restores nitrogen levels. Mulch is applied to the base. This barrier locks in soil moisture and suppresses competition from weeds. Visually, the contrast is stark. Crimson stems against dark green foliage. It is a rugged, shade-tolerant machine that converts low light into high-yield sustenance. But the list of shade-adaptable crops continues with another specimen commonly found in temperate orchards. 4 hours of direct light. That is the absolute biological minimum required to sustain the sour cherry. Why do sweet varieties wither in the gloom? They demand solar saturation to synthesize high levels of glucose. But the tart variety possesses a unique metabolic resilience. It operates on a tighter energy budget. While industrial sweet cherries fail without 12 hours of exposure, cultivars like the classic Morello or North Star thrive in USDA zones 4 through 8. The physiology is distinct. These trees are compact biological units. They occupy less cubic volume than their sweet counterparts. This makes maintenance in restricted spaces, such as narrow urban plots, physically efficient. In fast motion, the seasonal cycle unfolds rapidly. White blossoms erupt in the cool spring air. By midsummer, they transform into dense clusters of bright red drupes. On the surface, the shade seems like a disadvantage, but inside the fruit, the lower temperature preserves structural integrity. The pulp stays firm. The flavor profile concentrates into a sharp, acidic punch ideal for processing into sauces and preserves. However, humidity is the enemy here. Without the intense heat of the sun to evaporate dew, moisture clings to the bark. Fungal spores wait for this exact opportunity. The grower must intervene. Pruning shears open the canopy. This allows air currents to act as a natural drying mechanism, sweeping away stagnant dampness from the center of the crown. Reproduction is autonomous. The sour cherry is self-pollinating. A single specimen is a complete production facility. It does not require a genetic partner to generate yield. The result is a reliable source of carbohydrates and vitamins, harvested from the dark corners of the land, and the next fruit that performs. "4 hours of sunlight. That is the only fuel the mulberry requires. Why cultivate a tree that thrives in the shadows? Because it converts limited energy into massive caloric output. Most fruit-bearing species fail without full solar exposure. This organism functions differently. It operates effectively in USDA zones 4 through 8, displaying a high metabolic rate even in partial shade. The tree acts as a biological colonizer. The root system is aggressive. It penetrates compacted clay or nutrient-poor sand with equal efficiency to access the water table. The shade actually serves a functional purpose. Direct, intense radiation often scorches leaf tissue and desiccates the fruit pulp. By growing in the understory or near structures, the mulberry retains its hydraulic volume. In accelerated motion, the leaves expand rapidly to maximize surface area for photon capture. But there is a chemical hazard to consider. The fruit contains potent pigments. Upon impact with the ground, the ripe berry bursts, staining concrete and stone with biological ink. Strategic placement is mandatory. This is not a tree for the driveway or patio. It belongs on the perimeter, where falling biomass turns into fertilizer rather than a cleaning bill. For sites with limited square footage, dwarf varieties solve the space equation. They maintain high fruit density without the vertical sprawl. The harvest window opens in late spring. Upon closer inspection, the fruit structure resembles a blackberry. The taste is a complex balance of high glucose and sharp acid, suitable for immediate consumption or preservation. On the surface, the tree sits quietly, but inside the canopy, a resource war begins. Local wildlife tracks the ripening spectrum. Birds identify the sugar spike immediately. Without a physical barrier, like a nylon net, the yield is lost to the sky within days. Labor input, however, remains minimal. A single annual pruning session clears crossing limbs to improve airflow. The plant heals its wounds and continues to expand. It delivers a heavy harvest from the shadows. One dense yellow sphere, that is the biological output of the quince. It represents the 16th candidate for low-light cultivation. While modern agriculture often overlooks this species, it remains a botanical tank, capable of survival where fragile crops fail. Why plant a tree whose fruit acts like a biological brick? Raw, the flesh is hard as wood and loaded with astringent tannins. It is impossible to chew, but applying heat changes the internal chemistry entirely. The hard cellulose breaks down. The white pulp turns a deep, translucent pink. This is not magic. It is the release of anthocyanins and the massive activation of pectin. For the grower, this means one fruit serves as a potent thickening agent for jams, preserves, and caloric storage. Most fruit trees demand high solar radiation. The quince operates on a deficit. 4 to 6 hours of photons are sufficient to drive the reproductive cycle. It thrives in zones 5 through 9, handling thermal fluctuations from freezing winters to humid summers without halting production. But there is a specific nuance here. Consider the variety known as pineapple. It is genetically wired for resistance. While other root systems might rot in damp, shaded soil, this cultivar extracts nutrients and expands. It converts wet ground into yield. In fast motion, the branches erupt with pale blossoms in the early spring. The flowers act as a beacon in the darker corners of the plot. On the surface, it resembles a misshapen pear, but inside, it is a long-term storage unit for carbohydrates. The maturation process is slow and deliberate. As the season ends, the green skin transitions to a glowing gold. The sensory impact is chemical. The fruit emits a heavy concentration of esters and essential oils. One ripe quince can saturate an entire storage room with a floral scent. The foliage also adapts to the environment. In direct, scorching sun, leaves lose turgor pressure and burn. In partial shade, they retain moisture. The canopy stays dark green and dense, protecting the developing crop. The tree does not just tolerate the shade, it utilizes the cooler temperatures to maintain hydration. It requires minimal input, produces high-value pectin, and stores for months. A critical asset for the diversified grower. Now we examine the next specimen adapted for the shadows. Three to 5 hours of sunlight. That is the absolute minimum required to sustain this biological machine. Most commercial fruit crops would fail under such energy restrictions, producing nothing but weak foliage. But the alpine strawberry is different. Why does this plant thrive in the shadows where others wither? It is naturally engineered for low light efficiency. While standard garden strawberries demand full solar exposure to pump water into massive fruit, the alpine variety adapts to the cool, filtered light found in forest understories. It is a tactical asset for the dark corners of a plot. Zones 4 through 9 provide the optimal climate range. The plant does not need an open field. It functions perfectly in the dead zones along northern walls or under the canopy of larger trees. Upon closer inspection, the fruit reveals its strategy. The berries are small. However, this reduction in volume is a trade-off for density. There is no watery dilution here. The taste is concentrated, intense sugar, distinct wild aromatics. The growth pattern also differs from industrial varieties. Commercial strawberries launch runners, aggressively claiming territory across the bed. The alpine strawberry conserves energy. It stays neat. It forms a contained rosette. This makes it manageable for growers working with limited square footage, but biology still requires resources. The substrate composition is critical. The roots require well-drained earth, heavily amended with organic material. Acidity levels should be slight. Water is the fuel. Consistent moisture maintains the hydraulic pressure within the plant tissues, especially during the peak growing season. On the surface, the soil may look stable, but underneath, waterlogging can suffocate the root hairs. To prevent this, a layer of mulch acts as a regulator. It stabilizes thermal fluctuations and minimizes evaporation in the shade. In fast motion, the production cycle is relentless. Flowers bloom, shed petals, and swell into fruit. Because the berries possess low mass, they ripen quickly. The mechanism does not stop. From late spring into the cooling days of early fall, the harvest is continuous. This is a functional ground cover that pays rent and calories. It turns wasted shade into a production zone. Even without direct sun, the food supply is guaranteed. Limited sunlight usually implies a failed harvest, but one vine breaks this rule. The 18th candidate for low-light environments is the muscadine grape. This is an evolutionary anomaly from the southeastern United States. The plant is biologically engineered to withstand high humidity and suffocating heat, yet it possesses a rare tolerance for photon scarcity. How does a vine generate sugar without full solar exposure? Efficiency is the answer. 4 to 6 hours of direct light are sufficient for this organism. Morning exposure is critical. It kickstarts the photosynthetic process before the midday temperatures rise. The optimal range for cultivation lies between USDA zones 7 and 10. This is not a delicate table grape. Upon closer inspection, the skin is thick and leathery. It acts as a biological shield against pests and fungal pathogens. In practical agronomy, chemical intervention is rarely needed. The plant defends itself. Consider the variety known as Carlos. It is genetically programmed for vigor and consistency. It produces bronze-colored spheres rich in sugar. These are processed for juice, fermented for wine, or consumed raw as a high-calorie energy source. But the structural load is immense. Drone view. The vines form a dense, heavy green wall. A simple stake will snap under the weight. You need reinforced arbors, heavy-duty trellises, or solid fencing to support the biomass. On the surface, partial shade seems like a disadvantage, but inside the plant, a metabolic shift occurs. With restricted light, the vine curbs its vegetative aggression. It stops producing endless foliage. Instead, energy is redirected. The sugar moves into the reproductive organs, the fruit. Pruning is mandatory during the dormant season. This mechanical intervention ensures airflow and triggers the growth of new fruiting wood. The roots demand well-drained soil with moderate fertility. There is a nuanced trap here. An overconcentration of nitrogen forces the plant to revert to leaf production. The fruit yield drops immediately. Precise nutrient management is key. Afternoon shade serves a functional purpose. It acts as a thermal buffer, protecting the crop from heat stress. This allows the flavor profile to develop slowly without scorching the skin. By late summer, the harvest is ready. Heavy clusters weigh down the branches. One vine transforms a shaded perimeter into a calorie-producing asset. This brings us to the next fruit that handles part of the process. Four hours of sunlight. That is the absolute minimum required to sustain this biological unit. While most crops demand total solar saturation, the loquat tree operates efficiently in the margins. It serves a dual purpose, decorative biomass, and a source of calories. Why do standard fruit trees fail in partial shade? They lack the energy to convert sugars. The loquat, however, adapts its metabolism to lower light levels. Originating in the dense environments of Asia, this evergreen has established a stronghold in the southern United States. It thrives in USDA zones 8 through 10, acting as a resilient engine for food production in subtropical climates. For the grower, managing light exposure is critical. In regions with intense heat, direct solar radiation becomes a threat rather than a resource. Unfiltered afternoon light does not fuel the plant. It scorches the cellular structure of the large, glossy leaves. Dappled shade acts as a protective filter. It lowers the ambient temperature around the foliage. On the surface, the tree appears merely decorative. But inside the developing fruit, a chemical process relies on this coolness. Lower temperatures allow sugar chains to form slowly and evenly, preventing the fruit from ripening too quickly and becoming mealy. The phenology of the loquat is inverted. Most trees go dormant as temperatures drop. This species accelerates. It pushes out fragrant blooms in late fall or early winter. By spring, the branches are heavy with golden orange spheres. This timing is strategic. It provides a harvest when typical summer crops are still in the seedling stage. Upon closer inspection, the fruit flesh is dense and wet. It combines the acidity of an apricot with the granular texture of a pear. Varieties like Gold Nugget and Champagne are selected for industrial-level productivity and high sugar content. Cultivation logistics are precise. The roots require rapid drainage. Standing water causes immediate rot. A layer of organic mulch is necessary to lock in soil moisture and regulate root temperature. The tree maintains a compact architectural footprint. It does not require acres of open land. It fits into tight urban corners, turning wasted shade into a production zone. This is a shade-tolerant asset that remains productive year-round. Zone 2. That is the limit of survival for most agricultural crops, but not for the chokecherry. This hardy shrub marks the 20th and final entry in the shade-tolerant inventory. It thrives across a massive geographic range, enduring the deep freezes of Zone 2 all the way to the heat of Zone 7. Why cultivate a berry that puckers the mouth upon first bite? Because in a survival scenario, biological hardiness outweighs immediate sweetness. The chokecherry does not need a pristine orchard. It is an edge dweller. In the wild, it claims the damp banks of streams and the dark perimeters of dense forests. It is genetically engineered for low-light environments. 3 to 5 hours of sunlight. That is the total solar requirement to trigger fruit production. In practical agronomy, too much exposure becomes a liability. Intense, direct radiation acts as a stressor. It desiccates the fruit pulp and damages the cellular structure of the leaves. The plant prefers the cool protection of partial shadow. By late summer, the mechanism of reproduction is visible. Clusters of berries darken to a deep, almost black purple. Up close, the skin is taut and waxy. Inside, the flesh is dense, raw. The taste is intensely astringent due to high tannin content. But this chemical composition makes them ideal for processing. When boiled down for jellies, syrups, or fermented into wine, the astringency fades, leaving a rich, concentrated flavor profile. On the surface, the shrub appears invincible against the cold, but underneath,